Hello everyone, my name is Anthony Shivakumar, and in this video I just wanted to basically break down how you could work effectively with electronics using, say, simulation, experimentation, and math. And I'm going to take a very simple circuit that's basically applies to almost every part of electronics. We're doing an RC circuit, so a resistor and a capacitor, and these are passive components, and almost any circuit in electronics can be basically boiled down to either a resistor, a capacitor, or an inductor. So this is the kind of circuit, whether you're doing signal integrity, high-speed design, you'll eventually boil them down to, oh, that's an inductive nature, that's a capacitive nature. You also have another part of the lump circuit model, such as transmission lines, that takes care of characteristic impedance and time delay. So those are the four main lump circuit model where you can pretty much classify or organize any behavior that's happening in electronics to one of these circuits. So what I have over here is basically a simple RC circuit, and I wanted to show you how you could go about understanding things intuitively, conducting experimentation and simulation to strengthen your knowledge. And I feel this is the best way to learn electronics, and more importantly to have a deeper understanding of why things work the way they are. So in a nutshell, I have a very simple RC circuit. Let me zoom in a little bit. This is a 47 microfarad capacitor, electrolytic capacitor, connected to a 463 ohm resistor, if I'm not mistaken. We can do some measurements just to double check. So I do have my output on, so I'm just going to put off all the outputs and just measure it with my multimeter over here. And yeah, it gives you around 462, 463 ohms. So what we're going to do over here is I'm going to simulate this circuit using Keysight ADS. I'm also going to create a mathematical model of this using just basic math and paper, something that you do when you're studying electronics, especially at school, or your first year of engineering, or even high-level physics. You probably would be doing some form of this circuitry. And then we will do the actual experimentation, taking examples of what we get from the actual simulation and experimenting it with the actual hardware. So right now, let me open up the circuit in a nutshell. So I've drawn the circuit. It's a simple RC circuit. You have a voltage input, you have the resistance of 423 ohms, and then your VC is 47 microfarads. So this over here is around 47 microfarad. If you just look at 16 volts, 47 microfarad. 16 volt is basically the capacity at which you can charge this capacitor, and if you go more than 16 volts, it won't be able to retain that voltage, and it will blow up. So this is a simple circuit, and by basic analysis you can VI minus VC, there's a voltage across the capacitor, the voltage across the input. You subtract the voltage and you divide it by R, you'll get the current. And here the IC is equals to C dVc by dt. I do believe there's a little bit of buffering going on, so I just want to correct something. Okay, so yeah, IC is equal to C dVc by dt. That's basically the current flowing through the capacitor is equivalent to the capacitance of the capacitance value and the rate of change of how the voltage is with respect to time. And because IC is equal to C dVc by dt, you basically C dVc by dt is equals to VI minus VR, and then you basically organize this equation, and then you'll get dVc by dt is equals to, this is basically a state space model where you have the ABCD matrices, and that's really the mathematics of it. So A is equals to minus 1 by RC, B is equals to 1 by RC, C, and D. So what we'll do is we'll just take this over to MATLAB, which is pretty much the tool for doing this type of stuff. So I've written a very simple script where I have my R is 493 ohms, the capacitor is 46 microfarad, and the A is -1 into R into capacitance, which we have basically seen in here. So A is equals to -1 by RC, and here we have A is equals to 1 by RC. B is equals to 1 by RC. There's a negative sign in front of it. B, C, and D. And the C is 1 and D is 0 basically. Because if you do state space, you know that the input is directly equivalent to the output, in the sense over here we have VC is equals to 1 VC, and there is no input that we have that will affect the output, kind of a thing. And then you have some scripts to basically generate the plot. So if I do a step response, this is a step response over here in MATLAB. So what we have over here is it takes around 0.1 seconds to 0.2 seconds to reach steady state. So anything less than 0.1 second, if I start switching, you won't charge the capacitance to the input level, so the step response. So it's basically from 0 to 1. If I give it 1 volt, it should charge to 1 volt around 0.15. That'll be steady state onwards. We also have the frequency response, which is the Bode plot. We'll get into this shortly, but this is how the mathematical way of representing the circuit. Another way of representing the circuit is through using spice models. So you can use this using any spice model. So what we have over here is a simple pulse modulator over here. It's creating a pulse, high and low, and I have a RC circuit. R is 463 ohms and C is 47 ohms. It's a very simple circuit, but as I mentioned, these lump circuit models are, if you boil down any signal integrity issues, you'll basically boil them down to either RC circuit or RLC circuit, and they will just keep popping up. So this is a very simple, but it's a circuit. It's worth understanding it as deeply as you possibly could. And after you do the simulation, it's a transient response. I have the simulation over here. So this is very similar to what I have in the setup in my lab setup right now. So what I have over here is a pulse. I'm just gonna center this out properly. I have a pulse, and we're going with the square wave, and it's approximately. So here they have it as 10 volts. I could actually minimize this to 5 volts. Because I think I do have it at 5 volts over here. We can do the simulation again. You can press this button, and here we have it at 5 volts. So at 5 volts, it's going from 0 to 5 volts. I'm just going to put this as 0. So we'll just manipulate this and put this as 0. Yeah. So it's going from 0 and reaching to 5 volts. It's not yet completely 5 volts to 4.77 volts, and we'll see the simulation to see how accurate this in the real life example. So with the ideal situation of an RC of exactly 47 microfarad with a 463 ohm resistor, you're looking at this type of graph. So that's the second way of analyzing your circuit, is using a spice simulator and figuring out what your circuit is doing, your behaviors, give it different inputs to see how it's behaving. And you also have the mathematical representation if you understand how to derive the circuit using pen and paper. It gives you even much more stronger feeling of that if your math solving it by yourself matches the simulation, is great, and now if your simulation matches the actual experimentation, it really strengthens your understanding at a deeper level. So that's really what we're trying to aim at over here. So now let's go to the circuit itself. So as I mentioned, this is the simple RC circuit, and I have a signal generator right now present with me. So what I'm going to do is I am going to just show you my setup right now. I'm just going to connect my camera. So this is the circuit that we have over here, and what I have over here is the function generator. It's generating 5 volts, 5 hertz, and it's generating a high level of 5 volts. And this is the oscilloscope. I can show the oscilloscope on my screen. So this is the function generator generating the pulse width, and we can also generate a sine wave. So if I go over here and generate the sine wave, it'll immediately show the sine wave. And this is important for Bode plot to understand the frequency response of this circuit. So we're going to do both the analysis right now. So I'm going to go back to the square wave and then we'll analyze it from that perspective. So this is the circuit right now. This is the oscilloscope that I can show it on my screen. And what we have over here, let's match it with the actual experimentation. So this is channel 2. Channel 2 is the output and channel 1 is the input. So the input, I'm basically connected the signal generator input to the signal generator to the oscilloscope, and the signal generator output to the oscilloscope input. So I'll just show the circuitry once again. So what I have over here is the output, and this is directly going to be connected to the input of the oscilloscope. So that will give me the step response, the actual square wave. And the second part, the second output over here is now connected to the input of the circuit over here. And once it's connected to the input of the circuit over here, then the output of the circuit is connected to this part of the oscilloscope over here. So that's what we have over here. So that's how we have these two waveforms. The input is the actual square wave directly connected to the oscilloscope, and the second part is connected to from the output of the circuit connected to the oscilloscope. So let's analyze it using the simulation. So the channel 2 shows that the peak-to-peak voltage is 4.8 volts. So the top voltage is 4.4 volts. And I got the simulation with my LT with ADS pretty much the same. The high is 5 volts. The rise time and fall time in this particular analysis is not important, but there will be an instance where I will be talking more about rise time and fall time, how important it is, especially when we're talking about ringing and things that can cause how the impact of rise time and fall time in circuit analysis, especially for high-speed designs. I won't say high-speed design, but for anything that switches from from one voltage level to another voltage level, how quickly. So, but in this particular circuitry, the rise time and fall time is kind of negligible because it's so small compared to the RC time constant, which is almost like 1 second, and you're dealing with nanoseconds, so it's not really going to be much of an impact. So what I have over here is the voltage is 5 volts, which is very similar to my what my signal generator is outputting. And we have the pulse width is 100 milliseconds and the period is 200 milliseconds. So to understand that, so we'll just go into channel 1, with channel 1 is the input. So we have the width is 100 milliseconds and the frequency is 5 hertz. And 5 hertz is basically 200 milliseconds. So that's what we have over here. So 200 milliseconds is the period and the width is 100 milliseconds. And it's switching as the actual square wave. And when we do the analysis in Keysight, this is what we have over here. So let's zoom in and see how accurate it is. So at the highest level, we have approximately 4.93. It's almost reaching there 4.19 in an ideal 47 microfarad. Whereas in the simulation or in the experimentation, we don't quite reach very close to the 5 volt. It's the top is 4.96 volts. No, this is channel 1. So let me go to channel 2. Oh, that's my camera. So in channel 2, the top is 4.4 volts. So and the maximum is 4.52. So there is some practical things that are impacting the voltage from reaching that 4.9 volts that the simulation basically shows over here. So if I put this over here and it's charging, by this time it should be around 4.49, where in real life, in this particular, this capacitor, which I basically bought a very cheap capacitor, it probably is not the perfect 47 microfarad capacitance, and it's it probably might be a little bit more than 47 microfarad capacitance, and you can see that it's basically not charging to this full capacity. So experimentations can also validate whether you're selecting the right components when you're doing your PCB analysis. So that's another reason why doing these experiments is important, so that if you're selecting this capacitance and it's not producing the results that you want, most likely you've chosen a cheap capacitance and you want to go with a higher tolerance, something that really does not is close to what the simulation results are. Another thing that I wanted to talk about is this frequency response. Now in frequency response, what do we have over here? So in a straightforward answer is, if I keep changing the frequency, which is a sine wave, if I give it a sine wave, you're basically trying to figure out how well the system responds. So if I give it like 1 hertz, 10 raised to 0 is 1 hertz, it should basically be, the input and the output should have the same voltage. It should be like 5 volts, and there'll be some form of phase degrees that it'll be basically lagging the circuit. And as you keep increasing the frequency, the amplitude keeps decreasing, and this is what I want to show you over here. So let me go into the in here, and I'm going to turn it into the sine wave. And right now I have it at 5 hertz, and you can already see that at 5 hertz this is not equivalent to the actual magnitude of the inputs. The yellow line is the input and the output is the purple line. So at 5 hertz that we're looking at 0, this is 1 hertz, 2 hertz, 3 hertz, 4 hertz, 5 hertz. So at 5 hertz you're already looking at a gain that is significantly lower. Yeah, my camera is constantly beeping, and that's what it shows over here. So one thing that we could do is try to bring it at 1 hertz and see if it matches it. Now 1 hertz is pretty small, so what I'm going to do is bring this to 1 hertz, so you can see the gain will automatically increase. So you can see it's increasing, and this is at 2 hertz, and here we have it at 1 hertz, and it's almost following the output. So I'm just going to just bring the resolution a little bit further, and you can see that there is a phase shift, but the input is almost matching the output. Now this is not a perfect capacitance, so there's still the amplitude is still not as much as is not quite the input, but it's very close. So but there is still a phase lag. So at 10 raised to 1 you should not have too much of a difference between the input and output amplitude, but there is a phase difference, and that's what we have over here. So that's at around 1 hertz, and you can see that there's a phase difference, and the phase difference is approximately minus 10 degrees or little less than 10 degrees. That's so the input is lagging the so the output is lagging the input. So now what if I increase the frequency? And so what if I go to 10 hertz, and then we should see the amplitude drastically decreasing. And if I go to 100 hertz, it's going to be almost flat. So you almost have a high pass filter, because if the frequency keeps increasing, it's not going to respond after that. So let me increase the frequency. So it's going to be 1 hertz. This is going to be 2 hertz. This is going to be 3 hertz. I'm just going to put this as channel 1, and you can see the frequency over here is 3 hertz. And right now it's at 4 hertz. Now it's 5 hertz, and you can see it constantly becoming smaller and smaller. I'll just basically make this a little bigger so we can see this. And as I keep the amplitude, the magnitude is constantly decreasing. The input will always be the same with 5 hertz input, but as I keep increasing, now we're at 10 hertz. And you don't have to do this into in every frequency. This is what the Bode plot does, is basically giving you a spectrum of the frequency response, and that's why it's such an important tool to use, because you may not have the instrument to go all the way to say thousands of maybe even a gigahertz, but this mathematical analysis is already giving you the spectrum. It's basically saying from very small to very high, this is how it should behave, and from here you can actually see that. So I can keep increasing it to 10 hertz, and then we'll go to 100 hertz. I'm just gonna go to 1 0 0, and that should be 100 hertz. And and now you can see it's almost like it's like DC right now. it's very flat. So if you have very high ripples, it'll still smooth it out, and anything beyond that is just going to be very smooth. But it's not giving you the 5-volt output anymore. It's the output is let's have a look at what the output is. At channel 2, the magnitude or the amplitude of the signal is, I think it's having a hard time calculating it. Should be like 2, 3, 4, 1, 2, around 3 volts, I believe. Approximately 3 volts. And if you look at the MATLAB response, you're looking at this is around, so if this is 100 hertz, 10 raised to 0, 10 raised to 1, you're looking at the magnitude is significantly smaller. So this is the output over the input. You can see that it's yeah, it's tapering down quite a lot. So yeah, that's really it. So in a nutshell, what we've shown over here is you can, if you have the right experiments and you have the right equipment and the right tools to do the simulation, doing all 3 forms of analysis, which is the mathematical analysis, doing the experimentation and the simulation, really helps strengthen your understanding. And I think amongst all 3, the simulation and the experimentation is really motivating, but the math helps you truly understand what's going on at a deeper level, because now you're calculating things in your mind to really get to understand what these lump circuit models are doing. So that's really what this video is all about, is to show you if you're getting into electronics, these are the 3 ways in which you should be working to strengthen your knowledge. That's all there is from me, and see you next time. Thank you.